give this talk, even though I'm not in Brazil. I appreciate very much broadcasting, online broadcasting. I watch what happens there. So today I would like to talk about real-time dynamics in strongly correlated Fermi systems. And so this is a part of a bigger project that many people is involved there, mainly people from Warsaw, like me or Piotr Magierski. He had a talk Tuesday, Kazuyuki Sekizawa and Maciej Marchwiany. And there are also people from US, like Aurel Bulgak, Michael Forbes, and Ken Roche. So in this talk, I'll be interested mainly in fermionic ultra-cold atoms. Okay, we have two families of atoms, bosonic and fermionic. The bosonic atoms, they are typically well modeled by Gross-Pitajewski or Z and G method. Probably there were some talks about this. While fermionic systems, this turns out to be very challenging to describe for many body theory. And especially when you think about unified description of static and dynamic properties of large Fermi systems. Okay, so this is what we would like to do eventually. Simulate qualitatively, simulate at level of qualitative accuracy these systems. Precisely, I'm interested in cold atoms near a Feshbach resonance, or often they are called unitary Fermi gas. So just in case to remind you, that's the situation where the interparticle distance between atoms it's large in comparison to effective range. Okay, so Kf essentially describes the interparticle distance, and at the same time the scattering length it's large in comparison to interparticle distance. So that means that the system is dilute, and at the same time it's strongly interacting. And in this particular case, there is no length scale except density. So basically we have exactly the same length scales like in a free Fermi gas. So that means that physics behind the systems is quite universal, and it can be related to other systems, not only ultra-cold atoms, but also to neutron matter or high-temperature superconductors. Yeah, so the interaction looks to be very simple, but it's very hard to solve this problem because it's non-perturbative. Okay. Of course, we know that these systems are superfluid at very low temperatures, and we have a direct manifestation of this just by creating the vortex lattice. What is interesting about these systems is that they have extremely strong pairing correlations. So if you look at the ratio of the pairing gap to the Fermi energy, it's about 50%, so it's huge. Okay, essentially, that's the system with the biggest pairing gap in dimensionless units from all known systems that we have in nature. So to describe the system, I'm going to use method that is based on density functional theory. So just very, very simple introduction to this method. Basically, presently we look at this approach like an alternative framework to Schrödinger equation. Okay, so basically we would like to solve this problem. That's the Schrödinger equation for many body system. And this is framework. Framework in this sense that if you want to do something with this, first of all, you have to define your system. And you define your system by providing what is the interaction. Okay, interaction defines your system. So basically, I would say it's rather easy to provide interaction and stick it here. The problem is how to solve this equation. That's really hard. From point of view of density functional theory, the situation is slightly different because now it's again framework. So first of all, you have to provide energy density functional. And Hohenberg-Kohn theorem says that this functional exists. So for each system, we can define such functional. Okay, so So there exists such functional that defines your system, and it's universal. So you have to provide it to this framework. I mean, the problem is that there is no prescription how to derive it. Okay, so here we have a problem how to derive the energy density functional. I would call this part that it's hard. But once we have it, then solving of emerging equations, this is easier part. So this we can do it in practice. Okay, so basically when I say hard or easy, I mean in most cases just solve the many-body Schrödinger equation, it's almost impossible. While this, I will show in a moment that it's doable. I mean, we can do it for realistic systems. I'm not going to provide you very detailed foundations for density functional theory. There was talk by Piotr Magierski Tuesday. He was talking about the application of the same framework to nuclear systems. So he provided you some fundamentals like a Runge-Gross mapping or a Kohn-Sham approach. So basically I use the same things. The difference is that now I use a different density functional that I use in my simulations. Okay, so the most important part is it's right now energy density functional. So I used density functional that was constructed by Aurel Bulgag and Michael Forbes a couple years ago. Okay, so let me give you a short introduction to this density functional. So first of all, instead of using densities, we introduce the wave functions, and we use these wave functions to parameterize our densities. Okay, so we use we call them quasi-particle wave functions. So we parameterize our density, and now sigma means spin up and spin down particles. Okay, so we introduce different densities for both components, Fermionic components, but we also construct from these orbitals other densities, like a kinetic density, currents, and we also construct density that we call anomalous density. This one is proportional to order parameter or pairing gap, I mean eventually. Okay, and having these densities, then we propose our density functional. So that's generic form of this functional. So what we have here. So first two terms, these are kinetic terms. Okay, so if you remove this alpha here, this part and this part, that's the density functional that you have for free Fermi gas. Okay, and we multiply this two elements by some function alpha, and now this alpha depends on a local polarization. So that's how I define the local polarization. So that's the difference between densities of spin up and spin down particles divided by their sum. Okay, so that's the dimensionless quantity, and we introduce this correction in order to correctly capture what happens if we go towards so-called polaron problem. So now the density of spin-up particles, it's bigger than density of spin-down particles. Okay, so in this picture, these are spin-up particles, this is spin-down particle. So we know that this is polaron problem and that this particle behaves like a particle that has some different effective mass. Okay, and this coefficients, they assure that we recover correctly this limit. Then we have another term, and now we use here the fact that our system is scale invariant. So I told you that this is a universal case, so the only scale that we have is basically density. Okay, so if you think about energy, you know that we know that energy should scale like, it should be like a function of free Fermi gas, energy of the free Fermi gas times some number. And in order to get this scaling, the interaction part, the part that describes interaction between particles, it can only appear in this form. So there is a density to power 5/3 times some function, dimensionless function, and again we assume that the interparticle density can depend on the normal interaction energy can be polarization dependent. And then we have another term. This term now corresponds to pairing correlations. Okay, so this term, typically it's negative, and it decreases energy of the system when the system becomes superfluid. And again, if we recall that, we know that the pairing energy should scale, that ratio between the pairing gap to Fermi energy should be constant. The only form that we can use for the coupling constant here in front, it's again there is some dimensionless function. So this coupling constant can be polarization dependent divided by density to power 1/3. Okay. And we have finally last term. These last terms are proportional to currents, and we introduce them in order to restore Galilean invariance. So this too comes from Galilean invariance. Now, so we have parameters here, like we have a alpha, here we have a beta, and here we have a gamma. So these are dimensionless functions, and what we do with these functions, we just use polynomials. We represent them by polynomials up to some order. So we have some coefficients. Okay, so we have to fix this coefficient somehow. So we fit coefficients of these polynomials to static properties. Okay, so first of all, we need equations of motions. So equations of motions we derive by we simply minimize energy with respect to densities. And since densities are parameterized by quasi-particle wave functions, we need to minimize with respect to this quasi-particle wave functions. And in this way, you get equations that you can write in this form. Okay, so these equations are very similar to Hartree-Fock-Bogolyubov equations, or in condensed matter community, these are called Bogolyubov-Dijen equations. Okay, so they have the same structure like Bogolyubov-Dijen equations. Of course, these objects, all of them depend on densities, and densities again depends on quasi-particle wave functions. So these are nonlinear equations. So these are coupled nonlinear equations that you have to solve self-consistently. The remark here that I would like to make is that the equations looks like BDG equations, but if you would like to generate BDG equations in framework of density functionals, so you should use this functional. Okay, so this functional, if you minimize it with respect to quasi-particle wave functions, here you will get exactly Bogolyubov-Dijen equations. Okay, so for example, here there is no self-energy term, so that means that in BDG equation, in BDG approach, all interaction effects are modeled through pairing interaction only. So one unphysical consequence is that when your system becomes normal, for some reason, this normal state is described as completely non-interacting model, right? Because then you are left only with this part. So the point that I'm making here is that this is actually more. We have more physics here than in BDG approach. Okay, so how we get this? How we fix the coefficients of polynomials? We fit them to quantum Monte Carlo results. So we have results of quantum Monte Carlo calculations, both for symmetric systems and for unsymmetric systems. So this is table showing what is the energy of the system containing with A, it's a spin up, B, it's spin down. Okay, so what's the energy of the system that contains different number of particles? And we fit to this numbers our functional. So we have a systems for that where we force that the system is a normal state. We can also do it in density functional. We simply stick by hand that pairing field is 0. We fit it to a superfluid solutions. We have quantum Monte Carlo results for systems that are confined in a harmonic trap. Right? So this is system confined in a harmonic trap for unpolarized systems. So that's the number of particles in harmonic trap. And these are predictions of quantum Monte Carlo. This is how the density functional reproduces these results. So there is a very good agreement. And finally, the density functional was tested against the experimental results. So this is example of energy. The crosses are experimental results measured by a group from MIT as a function of polarization. So that's the ratio between density of spin up to density of spin down particles. And this is essentially quantity that is proportional to energy. Okay, so the crosses are experimental data, and this line here, it's what the density functional gives you. So this is how the functional is constructed. So now we want to model dynamical properties. So we go from static description to dynamical, and it's done in a very simple way. We just replace the energy here by time evolution operator. Okay, and now everything becomes time dependent because your wave functions are time dependent. That means that the densities are time dependent, and that means that all of these objects becomes time dependent. So what we have to do in practice, we have to evolve them, and we have to evolve a lot of 3D nonlinear coupled partial differential equations. Yeah, and this is quite challenging from numerical point of view. The problem is that we have a lot of equations to evolve, and the reason why we have a lot of these equations is because if you look at the spectra of this matrix, of HFB matrix, okay, it has both positive and negative energies. To define densities, we use positive energies only. But the problem with the spectra is that up to chemical potential, the spectra is discrete. So here we have some discrete states, and here we have a continuum of states. Okay, and we evolve everything up to some energy cutoff, which is of order few times Fermi energy. Okay, but still the number of states that we evolve, it's huge because of this continuous of states that we have here. Okay, so if we work with a superfluid description, we evolve everything. If for some reason the system goes to a normal state, then the states do not contribute to densities, okay, and only states that contribute to these densities are these states, and in this case, we reduce to the well-known, let's say, Kohn-Sham approach or time-dependent Hartree-Fock approach. Well, number of states that you evolve, it's essentially, I mean, it's the same as the number of particles that you have. Okay, how many states we evolve? So to put this into perspective, let's consider the following case. So we do simulations in 3D, okay, and for this we use a spatial lattice of dimension nx, ny, and z in each direction. So suppose that I have a lattice 100 cube, 100 points in each direction. And if you count the number of states, it's 500,000. That means that you have to evolve in time about 2 million equations, which is a huge number. Okay, just to store these numbers in memory, you need like 30 terabytes of memory. So that's the numerical challenge, how to do it in practice. So it's clear that to do this, we need big computers, and we benefit very much from recent developments in high performance computing. So what I show here is the list of the fastest computing systems that we have right now. So the fastest machines are right now in China. We don't have access to this, but we have access to European one, So that's a computer located in Switzerland. And we also have access to Titan machine. So today I'll be showing results that are generated mainly by these machines. Okay, so now what we do, we would like to validate this method, this framework against some dynamical properties, just to check whether we can reproduce realistic experiments. And for this, we used a series of experiments that were done by MIT group. The first was done in 2013, and then there was another 2014 and 2016 with better and better imaging technique. Okay, so what was done in this experiment, it was, the experimental protocol was following. So there is an ultra cold cloud of helium atoms. In experiment, they have about 1 million of them. Next, this cloud is phase imprinted in a sense that the experimentalists, they shine light of the one half of the cloud. And what this light does, it works like constant potential. Okay, so here you add some constant potential. That means that your phase of your wave function evolves with some faster rate, because there's this extra potential, in comparison to the phase of the wave function that for a left side. Okay, so after some time you create that the phase of left and right hand side are shifted by some value. So basically they produce the phase shift that is close to pi between these two fragments, and then they put in contact these two fragments. So there's a contact between these two fragments, and what you have, you let the system to evolve and you see what happens. So basically this, if you have the phase pattern like this is what is called the soliton. So you phase imprint soliton, and then the soliton starts to evolve in time. Yeah, and in time the experimentalists, they just improve the technique, how they make pictures of the system. So basically now they are able to cut the system into slices and take a picture of each slice. So they have access to internal structure of the system. So basically they provide pictures where we see very clearly what happened inside the system, right? So just after phase imprint. So what I show here, these are images, experimental images of the central slice, showing what happens as a function of time. So that's the time, how it goes. So we see that something is created inside. We call it soliton. Then it evolves somehow. Then we have two dots, here and here. Here and here. And these two dots, we associated them with a vortex ring because we assume that it's, it's going here and then again moving here, and so on. And in the final state, we see something like a vortex line. Or if you just combine these pictures for different slices, so that's the tomography that they did, they can resolve internal structure of the system. So as a function of time, we see that there is a soliton, so there is some that has a planar structure and then decays through some different stages to some object that has like a vortex plus line shape. Then it decays to a vortex ring, and at the end it decays to vortex line. So this is actually very challenging for theory to describe all of the stages. We call it cascade, solitonic cascade, because the soliton decay over different stages to the final state. So that's what we would like to do in our simulations right now. So I'll give you a few details about the simulations that we did. So we used the lattice, well, not very impressive, 32, 128. But still, if you translate it to a number of equations that it will evolve, it's like 250,000. So we take this lattice and we confine atoms on this lattice in a harmonic potential. So that's the confining potential that we use. So all frequencies in each direction are different, similar to what happens in experiment. There is also some unharmonicity term that arises from gravity. If you're interested in derivation of this term, how it appears as a result of gravity, in this paper you can find it. And we also make phase imprint. And when we phase imprint, we assume that this phase imprinting it's not perfect. Okay, so we slightly tilt this phase imprinting just to break symmetries that we potentially can have in system. So right now the number of particles that we can simulate, it's like the number of spin up and spin down atoms, it's in total is like a 600. So this is what we do in these simulations. Okay, so these are fully 3D simulations. All symmetries are broken. So I'll be showing you movies, and I hope that they go smoothly. But before I show you a movie, I just show you the way how we present them. So you will see frames like this, and by blue, I just plot the pairing field. So that's something that shows you where the condensate is located. So precisely, it's a pairing field divided by the Fermi energy. Okay. If we find somewhere some vortex-like structure, some points in the pairing field that the phase rotates by 2 pi, we plot it by a red color. So here, for example, there is a vortex line that propagates inside the condensate. Arrows shows how the fluid flows around the vortex ring. And I also provide here information about the density. So this is a frame from the movie for a spin imbalanced case, that the number of spin up and spin down atoms is different. But this shows the surface where the spin down particles vanish. So all atoms with spin down are located inside the sphere, while all atoms with spin up atoms are located in this bigger area. Okay. So for spin symmetric case, these two surfaces will overlap. So that's what I'm going to show you right now. So now how it looks in simulation. So we put in contact two halves of the cloud. One was imprinted, so the phase was shifted by a pi, and that's how it evolves in time. So we see that we create some soliton, and then this soliton goes over different stages and finally decays to vortex line. Okay, that propagates in system. So this vortex lines start to oscillate in a system. So right now I can compare just frame by frame from this movie. I'll use slightly different visualization of this movie just to compare frame by frame with experimental results. So yeah, so at the beginning we see that we create some structure that has has a planar structure, exactly like in an experiment. So that's the soliton that we see, right? After some time we see that the punch here is generated. So again it agrees. Then the punch rises and it's bigger and bigger. Something starts to happen here, okay? And at some point we create this different object. So where we have like a vortex ring. It's the vortex ring, and here we have a vortex line. So we can reproduce this very peculiar feature that was seen in experiment, right? So we see how the fluid rotates. So the particles rotate here like this around here. Then there is like this, and then they rotate like this. Okay, so that's like a vortex ring plus vortex line. And then we see that it decays. So this part is removed, and we are left only with the vortex ring that is deformed, similar to experiment. And finally, this vortex ring decays to a vortex line. Okay, so the particle now flows. So yeah, so I think it's quite remarkable that we can reproduce all stages of experiment without adjusting any parameters. We do not adjust any parameters. We just take our functional, let it evolve. So that was situations for a spin unpolarized system where we had the same number of spin up and spin down particles. And now we move to a different regime where we start to violate this symmetry. So now we play with systems that have a different spin up and spin down number of particles. So typically what happens in this situation is so what I show here is a cross-section through over cloud for a ground state. So if you have a different number of particles, typically what happens, we see a following thing, that inside the cloud we create a superfluid region. So that's the pairing gap, and that's the local polarization of my particles. So here we have the equal number of spin up and spin down particles. So the system is not polarized locally. And all atoms that cannot find friend to create a Cooper pair are ejected outside. Okay, so here are located atoms. Sorry, here are located atoms that spin up atoms only. So basically, we have a shell that is in normal state. Pairing here vanishes. We have a superfluid state, and yeah, we have a coupling between these two stages. Okay, and this is called phase separation, and the phase separation was observed experimentally. These are again the experimental images from MIT experiment. Okay, and that's the condensate. So that here the system is not polarized, and this is the shell of polarized particles. So now we always have this interplay between the normal state and superfluid state, even at zero temperature limit. Okay, because that's the zero temperature calculations. Okay, so now I just repeat the same simulations for a spin polarized system. Total polarization is at 20%. So that's the number of spin up and spin down particles. So again, we see that we see some solitonic cascade, that the vortex, soliton decays to a vortex ring, and then the vortex ring decays to a vortex line. We see this phase separation, right? That we have this shell of the normal component here. And here we have a condensate that lives. Yeah, vortex, it's confined inside condensate. So we see the full cascade. Dark soliton goes to vortex ring, go to vortex line. So what is interesting, we see that now the vortex line becomes polarized. So this is the same, this is a different visualization of the same results that I showed here, but now what I plot here the local polarization. Okay, so that's the difference between spin up and spin down particles across the center of the cloud. Okay, so this is my cloud plotted by a black color, and that's the local polarization with discrete levels. Okay, so and here's the vortex line, and we clearly see that the core of the vortex line, it's polarized. The polarization, it's like between 20 to 30% in this case. So that means that the vortex drags particles inside once it moves. So basically, this is how it looks in simulation. So first of all, we create a soliton that it's polarized inside. It decays to a vortex ring, okay, and then vortex ring decays to a vortex line, and then we drag inside this vortex line the polarization. Okay, and so the vortex becomes polarized. The vortex core. And if you think about this, it can be easily understood just noting that the most energetically favorable place to store the excess of unpaired spins is in the places where there is no pairing field, okay, where pairing field vanishes. So this is either this outer shell or inside the vortex core. And that's how it happens that we have a polarization inside the vortex core. Now we increase polarization and see what happens. So if you increase the polarization even further, this is a case where we have a 40% polarization. We see that the dark soliton decays to a vortex ring. This vortex ring propagates, bounces, and propagates back, but we do not see that it decays to a vortex line. Okay, so there is no vortex line in the final state. And it's not because the condensate is too small to have a vortex inside, because we checked that we took a smaller condensate to check whether the system is big enough to be able to create the vortex line here. So it is big enough to have a vortex line. So we see that the last stage of the vortex cascade is suppressed, and we associate this suppression with polarization effects. And now we can go for even higher polarization, where we take a polarization to be 60%, the total polarization. So we have some small number of spin down particles and large number of spin up particles. And just to show what happens there, I plot. Here I plot again the local polarization of the cloud. Here's the shell of the normal state. Here's the shell where the condensate lives. So it's this part is superfluid. And what I show here, I show the phase difference in a pairing field. So here the phase is 0, here the phase is pi. That means that we have a soliton. Okay, there is the phase difference equal pi, so that means that here we have a dark soliton. This red color means, sorry, this means minus pi. Blue color means minus pi. Red color means plus pi. So that means that the phase difference between these two parts is 2 pi. And you can always rotate the phase by 2 pi, so these two cases are actually equivalent. Okay, so there is no jump of phase here. So this is a soliton. So I show how it evolves in time, both the polarization and phase. So that's the solitonic structure that it's created. It has a planar structure. And simply what we see, right now it's stable and it just moves from one side to another, and then it's expelled from the system. So in this situation, we even don't see the decay to a vortex ring. Okay, so now again, we associate it with polarization effects. That cascade of solitonic cascade is actually affected by polarization effects. So these are conclusions of my first part, let's say. So basically, DFT, we think that it's a good route for unified description, both for static and dynamic properties of large Fermi system. We think that we have a very accurate energy density functional that was validated against the static and now also against the dynamical properties. And we predict some kind of new effects that you can find if you repeat the same type of experiment, but in case of the polarized systems. So we see that the solitonic cascade is affected by polarization effects. So I see that I have a few minutes. So let's go to the last part that is very, very short, about challenge. What is the challenge that we would like to face right now? So if we look what happens in ultra cold atoms community, both in bosonic and fermionic cases, typically we see that the experiments with fermionic systems are delayed by a few years, right? So for example, vortex lattice was created in bosonic systems in 2001, in fermionics 4 years later. The solitonic objects like solitons, quantized vortices, and their dynamics, oscillations, were generated in the bosonic systems in 2009, in fermionic again 4 years later, and so on. And there's many other things that I do not list here. But what we also notice that in case of bosonic systems, the quantum turbulence, it's right now very active area, and the same we think that will happen soon in the case of fermionic systems. So here we have experiments about the quantum turbulence in 3D or 2D. People are very excited about these results. So hopefully soon we'll have some results here. And to describe quantum turbulence, this is actually challenging both, I think, for experiment, but also it's challenging for a theory. So right now what we did, we did some calculations just to check whether our method can simulate quantum turbulence state. So yes, with this method we have access to quantum turbulence. We can propose some protocol how to generate the tangle of vortices. So for example, that's our results, where we took two clouds. Basically, we repeated the same setup that I showed the movies a couple minutes ago, but now we collided two clouds with already vortex lattice inside, okay? And then we show that if you just put in contact two clouds with vortex lattice, these vortices start to tangle, and they form objects like a kind of like a spaghetti, and then they start to disentangle, and then again they form the vortex lattice. So basically, if you have many vortices, at some point their dynamics may become chaotic, and this chaotic dynamics, it's called the quantum turbulence. So can we expect something new about quantum turbulence in fermionic systems? So that's the question that we would like to actually answer. But we know that the very important process that takes place in case of quantum turbulence is a vortex reconnection. Okay, and basically we know how to induce vortex reconnection of two vortex lines in a cloud of ultra cold atoms. Okay, so it's enough if we put two vortices close to each other, so they will reconnect, they will create something like X, and then they will reconnect and then exchange topology. And so this we can do very easily in our simulations. What we see right now, if we play with vortices that they carry inside the polarization inside, so that's the case where the polarization is 20%. Okay, so what we see right now, we see that, well, it's very hard to get a reconnection of these two objects. Typically, you think that we see that they, are close to each other. It seems like they're going to cross, but actually they stop and they start to repel and then do not cross. They rather like to form the vortex ring or things like this. So we doesn't claim that there's no reconnection in case of polarized systems, but we see that this process, it's hard to get this process. So that's probably one thing that can influence turbulent regime, so that's the still open question. But unfortunately, to study the quantum turbulence in the Fermi systems, this is an exascale problem. So that means that we have to wait for more powerful computers to do this. So hopefully in future we'll be able to do this. So these are conclusions. So except this these 3 points, I add another one, that polarization effect potentially can change the turbulence in fermionic systems. So thank you very much for your attention.
Thank you very much.